Hey, welcome back. In this video, we're going to introduce the concept of probability. We'll make sure to talk about the notation related to probability, some of the vocabulary with probability, and how to compute the probability in some basic situations. In this video, we'll be using the definition of probability, which is a measure of the likelihood of a random event of chance or behavior occurring. Before we start looking at the notation and a couple of quick examples, let's talk about the basic rules of probability. The probability of any event must be equal to or greater than 0 or less than or equal to 1. And this statement simply represents the fact that our probability can be 0% chance of something occurring or 100% chance of something occurring. Also, something important to point out is that if we sum all the probabilities for all the possible outcomes in a probability experiment, the summation of all those probabilities must equal 1. All right, let's now talk a little bit about the notation. If we wrote something like P of E equals 0.20, what this would represent is the probability of event E. This is a little bit abstract to start, but you'll see in some examples I'll do right now what we'll put inside here. But just so you know, what this represents is the probability and I'll just say the probability of E occurring in our probability experiment we get is 0.20. We do know that this also could be thought of as 20%. So importantly, just to go to this notation right here in this conversation is the probability of any event occurring has to be between 0 and 1, including 0 and 1. By the way, if it's 0, there's 0 chance of it occurring. It's an impossible event. If it's 1, it's 100%. It's absolutely going to occur on the next experimental trial. But we can often use fractions, decimals, or percentages to describe these probabilities. But just to use this notation real fast, what this first statement is simply saying is that for any event, the probability will be greater than or equal to 0 and less than or equal to 1. And so again, we would read this statement as the probability of event E occurring is 20% or 0.20. And to help us understand a little bit better this notation in kind of a realistic example, if we were flipping a fair coin with just heads and tails, we would say, for instance, that the probability of flipping a heads would be 1 out of 2 or 0.50, which is the same thing as 50%. So again, just showing this notation real fast, this is probably intuitive for all of us. We have the option on a very fair coin that's going to flip either randomly heads or tails. We have a 1 out of 2 chance or a 50% chance of rolling heads. And so again, just to show this notation, this P with the parentheses is describing we're computing a probability. Inside here, we're just describing the event that we're computing the probability for. And just one more example so we feel comfortable with this notation. Again, we're going to talk more about computing probabilities very soon in this video. But if we were given a traditional deck of 52 cards, we would say the probability of pulling a heart. So in this case right here, we have 52 cards. We're going to randomly pull one card from that 52 card deck. We want to compute the probability of pulling a heart out. Now, to answer this, you actually have to know something about playing cards, and we'll get a little bit more into that, as I've said. But importantly here, the probability of pulling hearts, what we would do is compute the percentage or the relative frequency of hearts in that deck, and we'll define that in a little bit more in a second. But in this case right here, we know that there are 13 hearts if we go from ace to king in the deck, and there's a total of 52 cards. This represents, if I reduce this fraction right here, a 1 out of 4 chance, or as a decimal, that's 0.25, which equals a 25% chance. Now, I've written this as 13 out of 52 cards, and again, you have to know a little bit more about a deck of cards to answer this question, and we'll talk about that, a little bit more about that in a second. But the idea is we do know actually that hearts are one of the 4 different suits in a deck of cards. So it makes sense that we have a 1 out of 4 chance or a 25% chance of pulling a heart out in a random pull out of that 52 card deck. And before we move on to more terminology and examples, I just want to emphasize one thing. When we're describing a probability, it's going to be between 0 and 1, including 0 and 1 as possibilities. And we'll describe those as fractions, decimals, or percentages. Either of them is good, and we could be asked to describe them in either way. I'll also just reiterate, we would not give a probability as an unreduced fractional amount. We reduce that fraction, and again, as a decimal or a percentage. All right, in that example where I was looking at the probability of pulling a heart out of a traditional deck of 52 cards, I used this technique that I'll describe more clearly in computing that probability. It's important for us in the work of statistics. I want to clarify we're going to have two different types of probabilities. We're going with the classical method, which is more the logical way of computing the probabilities, but we're often in statistics going to be using an empirical approach where we're going to be approximating probabilities and trying to scale it to discussing a whole population from the results of data taken from a sample. But just to clarify these real fast, generally speaking, and this is with dice or other probability experiments that we'll have, the classical method of computing probability would be to, in a numerator and denominator, in the numerator to compute the number of ways that the event can occur, and we'll show an example of this in half a second, and divide that by the number of possible outcomes. So previously with the probability of the hearts, I had, well, how many ways are there to pull a heart out of this deck? Well, there was 13 ways because there was 13 hearts in that deck of 52. So from a 2 to a king or an ace or a queen, those are all the possible ways that I could pull a heart out. And the whole deck had 52 cards altogether. Okay, so we have that. We maybe understand that. That was the same as the flipping of the coin. But in general, when we're doing statistics, we're not going to have these kind of logistical or logic truths. Instead, what we're going to have is we're going to be finding approximate probability. This is an empirical approach taken from observations of data. And what we're going to do is compute the probability as the relative frequency of an event occurring. So when we're looking at data, we're going to see the frequency of the event in question that we're talking about, whether it be hearts or a heads. And then we're going to divide that by the number of trials or experimental trials. Or in other words, if we're looking at a data set, it's the frequency of the event we have in question divided by the number of data points. But really importantly for the work you've done before is that we're going to use relative frequency to compute the probability of a certain event, and we'll show an example of that very soon. There's a couple more things that we need to talk about just before we move forward, so you just have an introduction to this vocabulary. First of all, we have this number of possible outcomes. The set of possible outcomes in a probability experiment is called the sample space. And technically speaking, the event that we're talking about is the set of possible outcomes that we're desiring. There are a lot of things around the concept of probability that confuses a lot of people. Like for instance, if you were to flip a coin and flip it 90 times and it came up heads every time, some people think then that likelihood of flipping tails on the next flip goes up as we flip multiple heads in a row. But the answer is that's actually not the case. In every single instance with a fair coin, it would be a 50% chance of getting heads and a 50% chance of getting tails. Though we have this concept of the law of large numbers, meaning if we performed a probability experiment thousands of times, or importantly, the more times that we perform a probability experiment, we're expecting to see the empirical viewed data that comes from that experiment to represent the probabilities that we're computing. So again, to state the law of large numbers is that if we did a small set of probability experiments, we wouldn't expect to get the exact probabilities that we've calculated. But if we had a large set of experiments, we would expect that the probabilities or the relative frequencies that are showing up in that empirical data would equal or become very close to the probabilities we could compute. All right, one more concept and a bit of notation before we can tackle a couple more examples is the idea of a complement. We'll be denoting the complement with given an event with this little c that's floating as an exponent. There's a couple other different ways to do this, but for our use, we'll be using this little c right here. And the complement of event E is simply not E, or all the outcomes where E doesn't happen. So we just attacked an example where we had the hearts, so the probability of pulling hearts from this traditional deck of 52 cards. So the complement of that would be the probability of not pulling a heart out of that deck of cards. Important to this discussion, I want to just talk about how we can compute the complement. So first of all, we know that if we have an event, if we have all of these outcomes from the possible things that could occur from this probability experiment, and we have its complement, all of the other outcomes that aren't this event E right here, that is the full set of outcomes. Therefore, given our rules of probability, the probability of an event happening plus the probability of the event not happening must equal a full probability of 1. Or in other words, if we want to compute the probability of a complement of an event, all we need to do is take 1 minus the probability of that event occurring. This might look kind of strange, especially with this new notation, but we'll talk about this in our next two examples. All right, in this example here, we're rolling 2 fair dice. Importantly, if you don't remember, fair dice have 6 sides with the numbers 1 through 6 on them. What's the probability of rolling a sum of 5 or less? This actually could be a really important probability to compute. Depending on the game that you're playing, you might be like, oh my gosh, I'm going to be in trouble if I roll over a 5, or I'm going to take some kind of risk. Is it worth it? I need a 5 or less. So we need to compute this probability. This will actually be a classical method because this is not empirical evidence that we're creating an approximate probability for. We're actually computing a probability from these fair dice, and we can compute all of the outcomes and the number of ways that E can occur. So let's do the work of finding the probability of getting a 5 or less from this sum. In order to do this, we need to do the work of finding all of the possible outcomes and the number of ways that E can occur. And we could do this by hand, but I actually luckily found online this beautiful chart that shows all of the possibilities of rolling 2 dice. And again, the question that we're being asked to answer is, we need to find the probability of getting a 5 or less. So from this chart right here, first of all, how many do we have? How many options? Well, we see that 1 can be related to 1 all the way down to 1 to 6, and then 2 to 1, 2 and 1, or 2 all the way down to 6. This gives us 6 columns, and 6 rows each. We have a total of 36 possible outcomes from rolling these 2 dice. And now what we need to do is compute the number of ways that E can occur. In this case, it's the summation of being 5 or less. Well, if we look at this, we can see in that first column right there with the 1s, we can get 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and 1 plus 4 is 5. So we have 4 in that first column. And then we have 3 in the next column, and then 2, and then 1. If we add those all up, 3, 7, 9, 10, we have a total of 10 possible ways that our E, in this case, summing of 5 or less, can occur. And again, all we did right there was compute the number of possible outcomes. There was 36 possible ways to roll these 2 dice. And then we computed the number of ways our event E could occur from that sample space, or from that set of possible outcomes. Again, we were looking for 5 or less. We decided we had 10 out of the 36 possible outcomes were favorable to our situation right here. If we reduce this, we want this as a reduced fraction, we would get 5 out of 18. Again, just to talk about, we probably know this, to reduce the fraction, I'm canceling a factor of 2 between these. Or in other words, dividing both the numerator and the denominator by 2. If I reduce this, or find this as a decimal, I would get 0.277 repeating. We could represent that as a percentage as 27.7 repeating percent. All right, that wasn't super difficult. We were able to find that probability pretty straightforward. But let's say instead we were being asked to find the probability of rolling a value greater than 5 from this summation. So we want to compute the probability of rolling a sum greater than 5. What we could do is go back to that chart again and compute all the possible ways we could sum greater than 5, or we could use this concept of a complement. We know that greater than 5 is actually the same thing, maybe awkwardly, as saying not less than 5. And we know that this is simply the complement of this event right here. So we don't want that to occur. So our formula over here would tell us to compute this probability of being greater than 5 from the summation is to take 1 minus the probability of this event right here, or in other words, 1 minus this 0.277 repeating, which when I plugged that into my calculator, I got as 0.722 repeating, which we could represent as 72.2 repeating percent. And for a quick review, we compute this probability by finding the total possible number of outcomes, or the size of our sample space, we could say, the number of ways our event E could occur, dividing those from each other, making sure that when we give that as an answer, we have a reduced fraction, a decimal approximation of that, or the representation as a percentage. We can also use this idea of complements, and I just want to state that it's actually very often it will be more useful and quicker to find the complement probability and to use this relationship right here. Depending on the situation, I would say, again, if I had to find all the probabilities of greater than 5, if I know a lot about dice, I actually know there are less representations of that summation being less than 5. So I could focus on that. So then if I want to compute the probability of it being greater than 5, I simply can just take away from 1 the probability of rolling less than 5. And again, in this example, we got that was 0.272 repeating, or 72.2 repeating percent. All right, in this example here, we're actually looking at the results of a survey or a poll, probably an exit poll, given to 1,000 registered voters. They were asked which candidate they supported, whether they supported the school funding initiative or the business tax initiative. This is an important example because this is an example of computing probabilities with an empirical approach. So instead of taking the logic that we had from fair dice or cards or flipping a coin or something of that nature, what we have is our observed data that we have from a data set, and that we're going to approximate probabilities given this. In this case, we're being asked to find the probability that a randomly selected voter supports the school funding initiative. Important to this question, and what we're going to assume right now, we'll talk more about this in the near future, is that this probability that we're going to compute and whether it actually is representative depends on the method used to poll these registered voters and whether the size of this 1,000 is enough to represent accurately the locale where this election is occurring. But let's not worry too much about it. Remember, when we're doing this empirical approach to probability, computing the probability is the same as finding the relative frequency. So we need to find, in this case, the number of voters that support the school funding initiative and divide that by the number of folks polled in this survey. So in order to compute this probability, we just need to calculate the relative frequency given this data set right here. Well, we know that we had 1,000 responses. We have 1,000 registered voters who were surveyed in this exit survey here. And now all we need to do is compute the number of folks that responded yes to the full school funding initiative. And what we have is 300 plus 220 plus 70 plus 30. If I computed that correctly, what I got was a total of 620 folks agreed with the school funding initiative. We can reduce this down to 31 out of 50, which is the same as 0.62 or 62%. Again, this was very different than our previous examples because this is an empirical approach we're not going just with the logic of fair dice or a fair deck of cards. We're instead looking at the observations or the data that we've recorded, but this is simply just relative frequency. We have the number of folks who responded, the number of folks who said yes to school funding. That's actually very, very similar to that classical approach in funding probability. We need to represent that as a reduced fraction, a decimal, or a percentage. But also, I just want to talk about real fast, if we wanted to now find out the probability of folks saying no to school funding, we actually don't have to go back and count that column where they voted no. We can use the concept of a complement. So if we wanted the probability of saying no to school funding, that is the same as taking 1 minus the probability of saying yes to school funding, which we just calculated as 0.62, or in this case, it'd be 0.38 of 1 minus the 0.62, which is the same thing as 38%. And that should make a whole heck of a lot of sense. If we're saying that 62% of the folks said yes, well then, the difference between that and 100% should be the number of people who said no. And I think this gives a really good real world example, maybe something tangible about the concept of a complement, right? So if yes was, if we only voted yes or no, that's an important thing here. If yes was 62%, then no must have been 38%. And if this data is representative of the local population, then we can assume that if we walk up randomly to a voter in this district, we would expect it's a 62% chance of that person saying yes to voting for school funding.